Very happy to have you here for my presentation. I'm going to talk about neural architecture and robustness, and yes, this is going to involve several facets of different aspects. So first of all, I'm going to motivate why we are interested in robustness in general. And yes, I'm going to motivate this from a computer vision perspective, because this is where I think my expertise is strongest, but this might, like some of the findings at least that we're seeing, might extend to different domains. And then I'm going to show how this can be considered together in the context of neural architecture search, and how to optimize things jointly so that we actually can learn on the one hand about robustness, and on the other hand about how to optimize for it in a concise way. Okay, so I'm going to start with the motivation. Here, basically, I'm showing several applications in which we see that, and everyone who is working with machine learning in general knows that computer vision as a field has been revolutionized by machine learning even since 2012 already, with very high accuracies in applications such as image classification, but also object detection or semantic segmentation, where in semantic segmentation, the task is to predict a label for every pixel in the image. In detection, the task is to find a labeled bounding box that surrounds an image, and for classification, we're just on a high level interested in assigning one label for the entire image. So no matter what the granularity, all these applications have been benefited a lot from machine learning, and of course, neural architecture search has been an interesting question in these domains, just because like building architectures is kind of difficult if you have to do it manually. It's a cumbersome process. Okay. However, very recently the story keeps changing, right? So we have been hand designing architectures to become better and better, and now there are these huge foundation models coming up that even allow us to do very good, like zero-shot classification. So we have very large pre-trained models that perform well in a general purpose setting, and this general setting is often referred to as zero-shot classification. So, for example, here like image classification, where you assume that you're just pre-training a model, and then you're starting to classify images, even follow-up models segment images or detect objects, without having ever seen the considered labels before, in particular during training. So one of the most recent very successful models is this contrastive language image pre-training model CLIP by OpenAI, which basically has a text encoder and an image encoder, and is trained on a huge amount of paired image text pairs examples, and basically the model is trained to learn an alignment between these two representations, so that when you now see an image, you can basically at inference time, the next slide, at inference time you can encode your image, and you can now at inference time create a data set of labels, and then you generate text prompts that are really generic, just by saying a photo of an object that you're interested in, a photo of a cat, a photo of a cute puppy, a photo of whatever is the class that you consider, and the model will tell you how likely it is that this is the class you're looking at. So this is kind of amazing, because it was not possible before, and it has been allowing to go like into really nice results in particular applications, such as here emotion or sentiment detection. We have recently been using it to classify images that are like from a completely different domain. So these are queried from social media with respect to, so these images have been posted with respect to climate change as a hashtag, and the question that we wondered is, now this is really a range of images where we need open domain knowledge, so where like given classes can apply this and how good do these pre-trained models work. And we're seeing, so this is a different story, I'm not going to go too much on it, but what we're seeing is, of course, it can do better than what we had before, but there is still a lot of room for improvement. So if the task becomes very complex, if the data you look at is quite different from what you've seen in the training data. In particular, if you look at social media, images are more, are not really described in the tweets, but commented. So it's a different, like the information that is transported is different, so the correlation becomes different, and the alignment works less well. Okay, so there's still room for improvement, a lot, I would say. But these models change the behavior and how we look at machine learning. Another point that has been criticized a lot in the literature is the robustness of these models with respect to text that is visually displayed on images. So as soon as you have text on the image, a classifier would tend to give a high correlation from text to text and not from text to image. So in that case, you're going from cache to voice, just because you write them. Okay. Second example of one of these very important large pre-trained models is the segment entity model. You also probably have all heard about it, you have maybe all tried it. It's again a large pre-trained models that now solve the task of image segmentation in a very reliable way. You can prompt it by having allocating a single point, and you're asking the model to segment the object this point belongs to. You can draw a bounding box and get very good segmentations. And you can even give it an image generic like this and ask to segment it into meaningful parts. Works quite well. So I don't know whether I have time to actually show the demo they put. It's an impressive look, right? So basically, very easily you can delineate objects from the background, and this works at different levels of granularity. Very nice. So the question it raises is a bit like, why do we still work on isolated small models that we can hand design and tune? One of the arguments I would have is that even if you look at these large nice fonts, such as sun, if you confront the model with the kind of noise that it has not seen during training, so this is really just short noise, but can be anything, right? So any kind of noise that it has not seen or not seen that dominated during training, the quality will delineate strongly. So here it basically does not work well anymore. So it's not as reliable as we want it to be, and for these large models, it's kind of hard to assess how reliable they will act in practice. How reliable they will act in practice. Maybe on the next example, maybe on a different kind of noise, it worked really well. So I'm not saying it does not work. I'm just saying we need to question how well would it work in practice, and how reliable will it be for our application that we're interested in. So, and now I'm giving a last example, which is one that we worked in while I was a postdoc in private. So we were creating a model that can compute optical flow. So optical flow, the idea is to describe the motion that is happening between two consecutive frames in a video. And if you look at this frame, you can see the overlay of two consecutive frames here. The arms are moving upwards. You can see the overlay of these upward moving arms. And the task is then to describe the motion between the two frames by a dense vector field that describes the motion in between every frame and the consecutive frame. Usually we use such a color wheel to indicate then the vector direction and length, where white means nothing is moving at all, and the stronger the color, the larger the motion, and the color, like the chromaticity, tells you which direction the object is moving into. So red would mean moving to the left, and cyan would be moving to the right, green moving to the bottom. Okay, and if we compute this now for the jumping jack person here, you can see that it works quite well. Yeah? So the arms are colored in blue, meaning an upwards motion, so this is correct. And then the left and rightwards motion in the legs also correctly. This is a good example for this image, which in an abstract way is difficult for many previous models because of the static background. And again, there is a video from our paper that shows how well this works if you if you do it in the wild even, but also on the standard benchmarks, it's much faster than previous methods. Okay, compared to methods that have been published before 2017, but actually it gives very robust and nice results. More recent models work again slightly better in background regions, also in describing getting the fire along the lines here. But overall, you see that this works quite well and stable. However, I mean, these are just some impressive numbers. So this was highly accurate in practice. It allows to compute everything very quickly. Like the paper has collected more than 3,000 citations of Google Scholar. We were very happy about this. And this is really comparison visually to previous methods. As I said, constant backgrounds have been very difficult for previous methods for whatever reason. The issue is what happens if such a model gets attacked. So here, that's a paper that came out in 2019, showing that if you insert a simple patch here, basically the optical flow prediction is destroyed not only in the region where the patch is inserted, but in basically the entire half of the image, so in a very wide region. So a small attack can really have a huge impact on the entire prediction and make it entirely unreliable. So you don't want to have your autonomous driving system employ anything like that where you don't know what's going to happen. So really, you really need to be aware that these things cannot happen in our models that we deploy in safety critical scenarios. Okay, so in general, we see that machine learning is only present in computer vision. To be successful, we all agree that we need our models to be robust in practice. And what I have been showing before is a so-called adversarial attack. You probably know roughly, you know more as well what this is. Here I give an example of this dog with the noise. So I don't know on which screen to show it. At some points not clear, but I'm showing that just let me directly know. Also interrupt me if anything is unclear. So basically for this adversarial noise, the idea is to optimize some small noise pattern with low, like really low intensity that can be added on the original image, and then your classifier will be full and tell a completely different label for the object. Here, for example, we have some noise that turns your puppy into an ostrich. Okay, this is a crafted example, but to visualize how important this is, just imagine you have a nice model that is trained on street scenes within Germany. There's a famous data set called cityscapes. You've seen an example from cityscapes on the earlier slide for semantic implementation. Many people like to train their models on cityscapes, but what if you then drive with your car, I don't know, from the Alps to Northern Africa, Morocco, where you have a high amount of sand in the air. All your noise models that you have been training with your model don't work out anymore. So current models are known to not generalize very well to such unseen domains. And these are examples from the ACDC dataset that has been created to facilitate evaluation of this behavior. Okay, so I was arguing for robustness. What is robustness? Let's try to grasp it. What we want is a model to behave in a stable way when we are adding noise to the data. So the model should not change the prediction all at a sudden. It should behave stably in the direct neighborhood of an image. So as soon as it looks similar, the output should be similar. And also when the data is slightly corrupted. I know whatever we mean by slightly, because the slight corruption is hard to measure in terms of absolute distances. So what you see here is basically, again, this adversarial example, where we're saying the adversarial noise, this is a small perturbation, and therefore it's covering the epsilon neighborhood of the original sample. So then we want to have a stable behavior. What you see below is an example of a data set that has been created to evaluate robustness to so-called corruptions, common corruptions. this is called ImageNet-C by Hendricks et al. And this is basically inserting into the images motion blur, zoom blur, and different artifacts that mimic behavior such as snow, and this is really added on top of the image later on, so it's just adding some flaky structures. But I mean, I would argue that we can still recognize the bird in all of these images, and we would want our models to do so as well, in principle. So we can, of course, evaluate on such common corruptions, just say, follow this idea, we create models, and then we just validate on data sets of given corruptions, whether they still work well. This is simple, and it's also informative. However, the expressiveness, I would argue, is limited. So because it's always predetermined by the set of corruptions that we anticipate. And it might be that there is a new corruption that we did not anticipate. For example, if you ask people in Germany, what should your model be robust to in terms of street scenes, everyone would say, well, if it starts to snow, I want this to work. But hardly anyone would think about sand in the air. And it's important, I'm sorry, it's still to work in these cases that don't come to mind directly. So what happens in the worst case, and this is again coming back to these adversarial attacks. So adversarial attacks are kind of designed to measure what happens in the worst case in a model. So basically, you assume that you want to add a hardly perceivable input perturbation within an epsilon ball of the original data that can fit the label, and you want to design or learn, optimize the perturbation so that it fits the label with this small perturbation. And the idea behind this is really to craft these perturbations as a probe, which is why you grant them for their optimization full access to the model. Now, you can argue that this is not realistic. It has been argued that in the use case that this is too hard. You would never face this difficulty. But if you understand it as really being a probe to your model, I think this has like high value to us. So we should consider these cases just to be sure what can happen and what cannot happen. Here's a short list of 3 such models that that are very commonly used. These are, well, the first is a white box attack, FGSM, which is a single step white box attack. So it assumes that it can use the gradients of the image to optimize the perturbation, and it proposes in a single optimization step the perturbation for the image. This is fast, and we like fast attacks because these are cheap to evaluate, so we can run many examples. It also means that we can use an attack like this to optimize our model during training. So we can use it in order to augment our training data to train a better model, more stable model. PGD is built up on FGSM in a way. It's a multi-step white box attack. So it can be a very strong attack. It takes multiple optimization steps. Also stays within the epsilon ball of the original image, and because it takes multiple steps, is a bit more expensive now, depending on how many steps you run to optimize it. And then usually we also evaluate our models using AutoAttack, which is the, so to say, standard for the evaluation of adversarial attacks on image classification. It's an ensemble of attacks that is like as one of the attacks it uses an adaptive PGD, which is a projected gradient descent with an adaptive step size, but it also uses a black box attack that doesn't even use gradients. So I have some more details on the attacks here. I don't know how familiar you are with these already, so maybe I can quickly say a few words. So this is just giving the update step for FGSM. As I said, it's a single attack, and it takes as input the original model's loss with the parameters, the image that has been fetched to the input, and the label, so the loss, and then it finds an update such as to maximize the loss, so maximize the model's loss. Now here we are actually just taking the sign of the gradient and not the whole gradient. This is for optimization stability. And then this is basically scaled by this epsilon, which is the parameter that tells you how strong the attack is about to be. So epsilon is usually chosen to be small. For example, for cipher 10, you would pick an epsilon to be 8/255, which is barely visible. You can see it barely visible. PGD then involves the same components again, but it's, as I said, it's an iterative attack. So it uses the previous time step of the optimized image, and again uses the variance loss of the optimized attacked image in order to update the attack to make it stronger over several iterations. And here alpha is the step size and epsilon is the size of the perturbation as before. The important thing, since we're taking several steps with the step size of alpha, we need to project the attack onto the epsilon bar after every iterations, and this is happening with this clipping operation. And yeah, then here below I'm sparing the equations, but this is an example for this black box attack, which is called square. It's a heuristic attack that queries the image, that queries the model again and again until it flips the label, and it has a heuristic of what rectangular shapes to add. Okay, so usually if you start evaluating a model with FGSM, there might still be some decisions correct. With PGD, many more decisions are incorrect. With auto attack, usually same epsilon, most models make mostly wrong decisions. So this is a very tough probe, and you don't expect this to work out unless you really confronted the image, like the model with adversarial examples during training. Okay, so now hopefully I've conveyed the idea that we need robustness, and for the rest of the talk, I want to show which of the neural architecture search methods that we know can be used, or I will give examples for some models to be used, so that we can actually optimize for robustness and that we can learn something about model robustness from neural architecture search. So the goal is to leverage multi-objective math in order to learn what makes our models robust. Do you have questions until here? No questions. Everyone's still tired from lunch. Yes.
I have talked about noise in images, but what about noise in signals, for example?
In time series signals,
yes.
Okay. Not an expert on time series, but in principle, what you see here, so these optimizations don't assume that you have an image. And so this is very generic. What they do assume in this simplistic form is continuous input. So I'm not sure how easily this transfers onto text where you have a discrete token at the start. But if you consider a continuous time series, you could transfer these models directly. Yes.
So this is motivated by that in reality you have, for example, sandstone and stuff, but you're trying to reproduce or query the robustness with your noise example. How much does this actually reflect reality and measure, and like is that able to measure real things? What is robustness really?
I mean, I'm going to show some examples of data later on where you can see this is correlated, but of course it's hard to say that it's causal because real corruptions can be beyond epsilon bound. So here we are always assuming that you have an epsilon bound that describes your perturbation as being small, because then you can reason in a Lipschitz continuous way. You can say if my model behaves smoothly, then my prediction will not change as I add small perturbation. But in principle, it's following the intuition of human perception, right? So if you cannot perceive the change, then your model should not be something completely different. It should generalize to these cases. And now, if we look at model behavior, we find that humans are surprisingly good at that. Why are we? Maybe we have seen so many examples, but it seems that we're really good at generalizing, and our models include it. But I'm not sure that answers entirely what you're saying. I'm following that in the end, it's not giving you a guarantee for a model to behave well under a sandstorm. But if your corruption introduced by the sandstorm is below a perturbation size of epsilon, then your attack model would have covered this point because it's optimized to flip the decision if it can.
Yeah, but I understood the idea correctly. This is more like real world examples, and this is the practical way to get them to work.
I usually motivated this.
Okay.
When it first came up, I think people were really shocked that like adversarial examples can fit network decisions so easily. So it didn't need a motivation from a real world. It's like a shocking property that you can just add something very small and get it really weird. That's a funny. It has been argued that this comes from that usually you argue that your data lies within a low-dimensional manifold inside a high-dimensional hyperspace, and this manifold might be, curved so that like very dissimilar classes can all of a sudden be very close to each other in a Euclidean perspective.
So, given that people can measure robustness, have people modified loss functions to include these things?
Yes and no. I mean, what you usually do when you use adversarial training, you basically include a few-step PGD attack or an FGSM attack in your training objective, and then you want your model to perform well under the attack and without the attack. And it's not that trivial. I mean, these things are tried, and I'm not going into detail here because it's very intricate. For example, just giving one example, turns out that if you train a model with an FGSM attack and you set the epsilon to the standard value, then you might end up with a model that performs really well on FGSM with the standard value, but not for FGSM with a smaller epsilon. So then you just can handle this one kind of corruptions, and everything on the surface of this epsilon ball works well. Everything inside, not so much.
Maybe as a follow-up question, does it also, if you train with these adversarial examples, does it hurt like on the original data set?
Yes.
Okay. Like a trade-off.
There's usually a trade-off, and I think it's also intuitively understood that if you have classes that are hard to separate, and then you force your model to, like during training, to work with corrupted data of these kinds, you basically force your model to overfit even more the training data to make the decision happen. So you have to be really careful. And then you can start designing dedicated training schemes that work differently on the hard classes than on the easy classes to avoid this behavior circular decisions. More questions? Then I'll move on. So just wanted to motivate now why looking into new architecture search in this domain, and before diving into it, just listing what else we could do. So many things could be done to address the problem, and many things have been done to address the problem. So on the one hand, we said we can change the training procedure, we can include it into the loss, or we can do data augmentation. And this is basically one of the examples that could be done for data augmentation. So basically you could say that's, if we have our training data that is all taken in nice weather conditions, let's take other images from a different source and stylize these images so that the content is the same, Also, the semantic boundaries are the same. However, now it looks like these images are taken in bright sunlight or in snowy weather or even at night. These stylizations work already quite well. They have limits, but okay, I mean, we could do these things and augment our training data. The one thing that is usually limiting is that we still have to be able to imagine whatever can come up. So we have to know beforehand what's gonna happen. And then this can be a good solution. Like if you know within my world this is the kind of like modes of variation I want to cover, you're maybe good to go. Another point that is interesting is to develop particular architectural design components. So of course you can say, let's look at every operation in my network in particular and ask why is this maybe prone to overfitting, to lack of robustness, and optimize on it. And yes, that also helps. In particular, it helps in combination with training procedures. We'll look at these things in detail. But the overall neural network architecture also matters, and this is where I want to head next. So the hypothesis would be that the lack of robustness in neural networks has not one but multiple causes, and we can of course address every of these separately, but the overall neural architecture design is important, and we should, or we could at least use neural architecture search in order to optimize these points and yeah, understand maybe a bit more on how things are interrelated. So now this brings me to the overall goals of neural architecture search and how this goes hand in hand with looking at robustness. So you all know that NAS is time consuming, and at the same time it wants to avoid a very time consuming trial and error process that is needed if you design things by hand. So basically when we're saying we want to do neural architecture search on our robustness, like on our model's robustness, then this goes in line with the overall goals. We want to find high scoring architectures now with respect to our new objective, model accuracy and model robustness. And then what we need to do in order to be good at that is to automate the architecture design process in terms of query efficiency. And now this becomes actually interesting. First of all, the question is on search spaces. So in NAS, we start from a given search space. This can be arbitrarily complex, but normally we, like in most easy cases, we consider some cell-based search space that allows us to easily mimic or model different kinds of architectures and use the cells then to build larger models from it. Then on a search space, we have a search strategy that allows us to draw an architecture on which we can estimate the performance with some means, and then use the performance estimate or evaluated performance in order to improve the search strategy. And this is where we want to be really efficient, because this performance evaluation is costly, and we don't want to do this too often and avoid it possible at all. Okay, so as an example search space, I'm referring to the last bench 201 search space here. I guess you all know this search space, right? Can I assume that? Okay, so very briefly summarize.
Maybe show of hands. Be honest, who's aware of that?
Who's where?
Who's not? Be honest.
I have it on the slide. I'm going to briefly go over it and you ask a bit more. So basically the idea is to compose research into these cells, or maybe I showed you the screen so you can all see my pointer. So basically you have this cell which enumerates operations that you can use, and you determine the set of operations to be either 1-by-1 convolutions or 3-by-3 convolutions, or an average pooling, skip connections, or zeroization, the removal of information. And then the idea is basically to use such cells in order to compose larger models by stacking your 3 times n such cells, one on top of the other, so that in the end you get a competitively large or deep model. That is, however, being subject to optimization on the cell level. So this is the cell you're optimizing in terms of its connectivity. In the end, you get a large model that you compose by stacking these operations one onto each other. In the end, we have a global average pooling here, which is the standard case for many image classification models. So in the end, you just take the global average of the features in order to learn your classifier on top. This is the standard, for example, for ResNets, but also vision transformers have been related with this strategy. It's the right thing to do. And yeah, so in NAS-2-1, you have this particular configuration with 6 edges for the operations, 5 predefined operations, and then this turns out to give you, well, in the original NAS-2-1 benchmark, more than 15,000 architectures. However, it turns out that in such a search space, some architectures are easily being isotropic to each other. So if you remove these doubled architectures, you can end up with about 6,000 non-isomorphic architectures. And then in the original NAS-2-1 search space, they provided evaluations, like weights for trained models for these architectures on Cypher 10 and Cypher 100, and on a low resolution version of ImageNet, which is here called ImageNet 16120. And it's a tabular benchmark, meaning that for all the architectures that we're considering and all the data sets, the evaluation in terms of model and performance scores is given. So you can basically just query the benchmark and get the evaluation of the model. So this is nice because it's small and contained and can be complete. There are other benchmarks that are very interesting, that are not complete. For example, in NAS-Bench 301, we tried to build a benchmark that covers the dark search space, but then allows for some performances to be estimated. And the other nice thing about NAS-2-1 is really that you can write the model. So if you want to learn more about the models, this is informative because we not only see the architecture, we also see what they actually learn. Okay, so now you've seen the overview. We know search spaces. Now there are of course many ways how to do your architecture search. We can just find an architecture, get its evaluation by training the model and running it. This is what I would call naive NAS, and this is of course very expensive because it requires you to evaluate the model every time. And this is also why in your architecture search, a lot, like most research is focused on how to speed up this process, make it work very efficiently. And yeah, so several methods have been proposed there. One very interesting line of work is this so-called one-shot NAS, where the idea is to really jointly search for an architecture and optimize the architecture at the same time. And darts is maybe the keyword most people know in this context. So basically, this is the figure from the darts paper showing how this basically works. So you assume that you have your cell given, you just don't know which operations to be executed at every connection here. So this is what you want to look for. And now in this dark line of work, the idea is to basically initialize all operations at every point, and then learn at the same time the parameters for every operations, as well as parameters alpha here, that give you a weight for every of the operations. And in the end, you train the alpha with the softmax. So this is all continuous, you can only run it end to end, and in the end you need to take the argmax operation for every of the edges to do a rounding. This, yeah. So this is the very simplistic unit. Like, of course, this relaxation is a bit loose, so a lot of research effort has been devoted into making this tighter, making it more efficient so that you don't lose so much in the rounding step. And yeah, to give very good results. The other line of work that facilitates a large speedup are so-called predictor-based models. So models that really have as a performance estimation strategy here very few actual functional evaluations, and then maybe train a performance predictor that works as a surrogate model for all the other cases, or even use a zero-cost proxy, like a proxy that only sees a very limited amount of data on an untrained model and then tries to predict as good as possible how well this model is going to perform on average. So these are these two groups: trained predictors, hopefully trained on very few samples, or zero-cost proxies that don't require a model training. So let's, for example, look into predictor-based neural architecture search. The idea would be to basically encode architectures here. So this side is basically shown to encode architectures. The example is on a graph-based encoding for architectures. It could be something else, but just consider this example. So you encode a model onto a latent point, and you can use a reconstruction loss in order to train that. You don't need any functional evaluations on that. You have to consider the model to be a graph that encodes its information flow. You do so, and then assume that you have some sparse evaluations here indicated by the red dots. From these, you can train a predictor that tells you how good one of these points is going to be, and then you can use your predictor in order to evaluate your points in your search space. So in that sense, you can consider it a classical two-step approach. You can have an unsupervised pre-training of the architectural latent space here, and then from Q predictions, you can run a predictor that allows you to do the optimization. Now, how to run the predictor? As I showed you this example of architecture graphs in the beginning. It can be such representation, but successful models have also been using different kinds of representations, such as adjacency matrices, very plain, so which operation comes after another. Also, path-based encodings have been very strong in the past. So one famous example would be the bananas paper. All have pros and cons, and again, very simplistic summary would be that if you consider adjacency matrices or path-based encodings, this can run into scalability issues if your search space grows, because then the paths you can enumerate at some point take too much space. On the other hand, these learned graph-based encodings need to be retrained for the new search space, so this is task dependent. The nice thing about these is, of course, you can formulate it in a closed form and just compute it, no matter what data. Okay, so depending on your choice, you encode your data into your latent space, and then you can start to search for it. For example, to query your architectures. What you need to be able to do, therefore, is to generate valid architectures from your latent space. And in this setting where we have the reconstruction loss, this is mostly the case. But this is something we need to be careful. We need to remind us, like, how valid will the architectures be that we query. Okay, so this is not one example of a graph encoder, where basically you have the input node here. Okay, sorry, I'm again showing it here. You have the input node here, most pointer, And then the information forward flow is modeled. So you're basically, for example, training a graph neural network with standard message passing scheme that encodes the forward path. And to be sure that this covers your data well, you usually also want to encode the backward path as well. So the path that the data follows in the back propagation, where the gradient comes from the output side and flows back. So then if you encode these two information paths well, you can create a latent encoding here, HG, which would then be one point in the latent space. And then, yeah, one standard way to optimize it then would be to run Bayesian optimization on the latent space. I think you have an expert talking about Bayesian optimization tomorrow or the day after. So this is just a very high level perspective on it, right? So basically the idea is then to fit some posterior distribution on the data and to use an acquisition function that gives you the next, like tells you how to sample in a clever way to get away with only very few samples that are in interesting locations to be very informative on the distribution and hopefully maximize your improvement. Okay, so yes.
Maybe a too detailed question, but for the embeddings, would you create those embeddings based on similarities, so same style of predictions, or performance similarities? So,
okay. Yeah, good question. The actual question is, what information do you have at hand? In many standard models, including ours, we are assuming that when we are training the embedding space, we don't know how good a model performs. So then it would be completely unsupervised. You're just saying this is the structure, learn that similar structures are nearby each other, and then at some point I give you a training sample and you tell me something about the neighboring ones. If you have more information at hand, of course you can use it, and probably that helps. Yes?
Yeah. I guess the assumption is pretty realistic that you don't have that a priori, right? So this is why you do it like that. So how about, is it possible to update it while you're gathering a little bit during the BO loop to update the embedding? Is that possible?
Yes, sure. I mean, yes. Basically, as soon as you are doing BO, eventually you are going to evaluate something, and then you can also backpropagate your gradient into the GNN embedding. And yes, I mean, as soon as you have such a GNN embedding space, you start doing that. So in our works, we did so. That's now a difference to adjacency-based methods, which basically have fixed embedding that is not learned. But then if you look at the strengths of path-based embeddings, they apparently were quite well developed.
Okay.
But for GNNs, it's definitely worth propagating it, yes. Okay. So now this is like basically standard overview of our neural architecture search. Now let's get back to robustness. So in order to do robustness and like to do neural architecture search for robustness, or to evaluate impact of robustness in our evaluations, we need some data. And we are lucky that now there are two data sets available, one of which we created ourselves. And this is this first example here that we presented at iClear 23, which is, yeah, just it has a quite humble title, Neural Architecture Design and Robustness, a data set. So it's really also nothing more than a start in that direction. There is this other example here, the data set identifying robust art, benchmarking robustness in architecture design and training techniques. Has been on archive for quite a while, and it's, I think, a very promising data set. However, quite hard to get access to the model weights actually. So it's the way it's organized so far makes it a bit tough to work with, but I'm going to show you what we have in our data set in a second, and then you understand why what they have is also very important. Okay, so the idea of our data set, this simple data set is to be kind of complete in collecting evaluations for robustness on an entire NAS search space. And this will help us to evaluate the complete search space and get insights into what happens if you change a detail in your architecture. What happens if the edit distance of my starting architecture and the next architecture I'm considering is really one, I'm changing one detail, will it have impact on what I'm doing? So the applications we envisioned were, of course, NAS for robustness evaluation, but also to design new proxy measures, hopefully that can let you know more quickly on the robustness of your architecture to come, and also how to analyze your design. Okay, and what did we do? We started off with the NAS 201 search space. So you remember this simple cell-based search space I mentioned before, for which many evaluations are given. And yeah, so these are an example, I think, for two models that one can consider. As I mentioned before, the full search space had 15 to 16,000 architectures. Not all of them are non-isomorphic. We just picked unique architectures. And then we actually leveraged the fact that the training weights are available for these, so we didn't have to retrain them. But what we needed to do is really collect data now. From these search spaces, we ran a huge evaluation of the models under common corruptions. So you remember these Hemrich's corruption types with the different amounts of blur and externally mimicked weather corruption types, color corruptions, and so on. And also with the standard adversarial attacks that we know about. So we have data from three different benchmarks. We have these corruptions to be added on all these data. And then we can use this in order to generate a full evaluation of how every of the models performs when facing these corruptions. Now, for the attacks, they have a hyperparameter, which is the epsilon value, that tells you how strong the corruption is. So here, for just as a reminder, I put it in the equation for FGSM. So for FGSM, we tested epsilons ranging from 0.1 to the largest reasonable value is 8 over 255. And then just as a sanity check, we also allowed for the maximum perturbation, which is 1, where a model can drop to random or even below. Similar for PGD, which is a bit more expensive, and therefore here in this range between 4 and 8, we did not sample the epsilons densely, but still have a quite solid coverage of the behavior of models on the different epsilons. APGD is a version of PGD with an adaptive step size, so this basically changes the alpha adaptively during running the attack, and is known to again perform more strongly than PGD. Again, we evaluated this for 0.1, 0.5, 1, 2, 3, 4, and 8 over 255, and again then the sanity check 255 over 255 to see that actually the model performance drops to random. And Square is a black box attack, like the last attack in the ensemble of auto attack from the standard benchmark. So we also ran this with the different epsilons and 5,000 search iterations for the black box attack, so that it performs strongly. Altogether, we have then a good coverage of the attacks that are given in auto attack. So again, auto attack is this ensemble of different attacks, consisting of 2 versions of APGD, and in the end they're running square. They are also running a tab attack in between, which is optimized to have a small epsilon. So it's not using a fixed epsilon, it's optimized to flip the model's decision at low change. So it's also an expensive attack. And in the first situation, we have it. Okay, and now what happens in terms of numbers? So this is just a plot showing the model prediction accuracies on average as you increase the epsilon. So in the first plot, I think I can draw this in. First plot here, we are showing the accuracy on side by 10 when running an FGSM attack. So the simplest of the attack, single step. With a small epsilon, the accuracy only decays a little from the initial one. As you increase the epsilon, this goes down drastically. And yeah, so with an average below 40% for the 8/255, and going to random if you reduce about epsilon. Now, this FGSM is again single step attack, not very optimized. If we look at PGD, a 40-step attack, this is much more severe. For its small epsilon, again, not so much happens, but as you increase the epsilon slightly, results drop super quickly. And even at an epsilon of 2/255, the decision is already below average. So below random predictions, and then basically the model manages to flip all decisions, so not come to an average prediction, but everything is predicted incorrectly. With APGD standard, I mean, again, it's like an optimized version of PGD. So you see the expected behavior; it's even more severe for 2/255 epsilon. We're already far below average prediction probability, and for 1/255, which is really tiny, tiny change in the image data, you have less than 20% chance of making a correct decision. Yeah, and the last point, interestingly, like the square attack, which is a black box attack but has a high budget, is of course also a strong attack. But the curve falls a bit differently than for the PGD one. So basically, in the like low epsilon regime, the networks can still predict quite well. Yeah, until say 1/255, you can still get something very reasonable from the model. Yes, please.
I'm not sure what you're saying. Sounds like
Okay, it's not a detailed question to these parts, right? It's like a high-level question. I would connect it rather with the field of certified robustness, and it's the more closely related field, right? And if you, so then the goal would not be to train a model to be robust, but to certify a model for a given robustness. That is related. Maybe you can discuss this after the presentation. It's a complicated question, I guess. So if you want to certify a model with respect to its robustness, basically you're asking, the model gives you a certain prediction, and you're asking the model how stable this prediction will be. So if I add an epsilon now, how long will the model say the same thing? In this case, we're asking, like, if I change, I'm asking in the beginning, if I add an epsilon like this, what is the chance that the decision does not flip, no matter what the decision was? So it's slightly different perspective, but it's an interesting relationship, I guess, between the two questions. Maybe you can discuss it in the following hour. Okay, so now we have all these simulations. We ran this was quite some compute time, and then we ran many evaluations. We computed now metrics like aggregate metrics and how to understand what we have. And you have these two plots here. One is for the common corruptions, one for the adversarial attacks. Let's start with the positive thing, like for the adversarial attacks. Everything that is blue is at least positively correlated. And now the robustness of a model evaluated under an adversarial attack with one particular epsilon seems to be, in most cases, positively correlated with the performance under a different kind of adversarial attack. In particular, all FGSM results are very strongly correlated amongst each other. The white bars here are what happens if you run the maximum epsilon to 55. So here the decision is always random, no correlation expected. FGSM and PGD also correlate strongly. If you want to know how well a model will perform under an APGD attack and a quite sophisticated attack, and you have only evaluation of using FGSM, this is not so strong indicator anymore. Right? So here, basically, you have this light blue area, which tells you you can say something, but not correlation is not that strong. But if you have an evaluation using PGD, and you want to know how well it works in APGD, there is some. This is already a quite strong indicator, and then for square attack as well. So in general, you would say if my model, if I have an evaluation of my model, one of these attacks, and I want to predict another, I can use the signal. For the common corruptions case, it's maybe more tricky. So in general, many of them are nicely correlated. However, here, for example, the Gaussian noise seems to be an outlier that is haven't correlated with any other, while the blur corruptions are correlated with each other. So there is some signal, but not everything translates one to one. Okay. What else can we consider? We also evaluated the prediction confidences. So ideally, if your model gives you a wrong prediction, you would want it to also say, I'm not confident. However, this is also one of the core issues. Our models tend to be very confident in all their predictions, even if they are wrong about it. And now we see here what happens if you increase the epsilon. So for epsilon being 0, like clean data, the correct class confidence is usually quite high, above 96%, and the prediction on incorrect classes is also high, like slightly below 80%, but it's at least lower than the correct class prediction. So something seems to be right on average. And now as we increase the epsilon slightly, the confidence in the wrong predictions also increases. So the model makes a wrong prediction, and it's increasingly confident by giving a wrong prediction until this point of 2 to 3 over epsilon, from which on the model seems to be not confident at all what it does. So this is maybe something good, right? So if the image is very corrupted, the model starts being not confident. And here it's just an example for the confidence progression over epsilon. So the example is just the class 0, where if you have no adversarial attack, the model predicts class 0 and is confident about it. And as you increase the epsilon, the posterior for the other classes starts to rise and becomes stronger and stronger, so that eventually other classes have like higher confidence than the first. Okay, so this general analysis. Now, what does it mean for architecture? So here you have examples of the 3 best architectures from the /2-1 search space according to clean accuracy, according to the mean adversarial accuracy, and the mean accuracy in terms of common corruptions. So we found this quite interesting because they all have like some traits in common. For one, so all of these have 2 stacked 3x3 convolutions. So start from the input, have a 3x3 convolution here, and have another 3x3 convolution there, and then a third one here. Here as well, you have the same path, and here as well. So a deeper model seems to be, in that sense, advantages over a wider model in terms of robustness, as well as in clean accuracy. Yes.
Do you know what the ranking of the methods was? For example, the first one, how it was ranked on the second or on the third task? Was it like bad or was it still good?
No, it's not bad. I mean, also these tasks are correlated, right? So the clean accuracy is kind of an upper bound for the robust accuracy in these cases where the models are not adversarially trained. You can expect the accuracy only to decrease, but if your model starts with the low clean accuracy, you will never get to very high robust accuracy. Okay. This is just, I mean, maybe this is related to your question, Abby. So this is just a plot of the of the edit distance one neighbors of the best model with very clean accuracy. So here on the y-axis you see the mean adversarial accuracy, here you see the clean accuracy, and now the neighbors of the best network according to clean accuracy are spreading along this axis here. So on the one hand, you see that both are correlated, right? So mean adversarial accuracy over clean accuracy, there's a strong correlation between the two. Then if your clean accuracy is good, it doesn't mean that your adversarial accuracy is good. However, if your clean accuracy is not good, your adversarial accuracy will also not be good. So you know that. Okay. So again, this is, I guess, quite interesting. And then the question is, what is the issue with these architectures that are very low in mean adversarial accuracy, so that are very close to the best and are, yes, there's a question.
Question about, as you said, this general problem of neural networks being overconfident in their predictions. And there is this technique of confidence calibration. Are you aware of how this translates to this problem or to this setting?
But, okay. Again, I think the answer is not simple. So the simplest thing you can do to calibrate the confidence is basically some temperature scaling. This will give you better calibrated confidence, but it will not change the behavior between a model being more confident in the wrong prediction than the right one, or vice versa.
So it behaves kind of the same.
Basically, you're shifting, you're rescaling the entire plot, right? Not linearly. But of course, the absolute value you will get will be better. So the absolute confidence will then be lower if you calibrate it before.
I'm just wondering whether this.
This is not relating to confidences. So we're just having on the y-axis the clean prediction accuracy, on the y-axis the mean adversarial prediction accuracy. So just showing if a model works well on clean data, does it also work well on attacked data or not? Yes. Okay. And I was just about to say, in particular, I would ask, why is this model so bad and why is this model so good? And so why is one model like keeping its accuracy under attack and the other is losing so much? To get more insights, we also looked at what happens if you use models that have the same number of parameters. So usually, like if you consider zero cost proxies, the number of parameters is a very informative indicator of how modern architecture will work. Now, let's just take this out of the equation and just look at what like the performance of models. This will give you a very low number of architectures to look at, and here you just see the evaluation of the top 20 architectures that have this this number of training self-kernel parameters. Okay, and yeah, again, this is the cell we are considering. So the operations are these indices numbers here. So the operation 1 is the one that is displayed here, that goes from input to this feature map 1. 2 is the operation here, that we're showing there. Sorry, switching in the second cell. Again, maybe I should. Yeah, and then on the y-axis here again, we see the mean adversarial accuracy. So what we want is a high value here. So somehow this dark red architecture here seems to work quite well. Now, what properties does it have? It starts with 3x3 convolution. And for the 2, like for this step here, like for this skip connection here, it actually has a 0 ice, so nothing is flowing here. Then operation 3, so going from 1 to 2, this is the operation here. We are again having a 3x3 convolution. So again, you see this pattern. We are stacking 2 3x3 convolutions. This seems to be very important to maintain robustness and in the sense like to have a deep model in a sense. For operation 4, which is this potentially this connection here that links input to output. It has a skip connection and operation 5, which directly goes also from 1 to the output, it even zeroizes the results, but when going from 2 to the output, so here, this operation 6, it again has a 3x3 convolution. So you see the same pattern as before. Now, if you look at the not so good architectures, for example, the dark blue here, it also even starts with 3x3 convolution and a zeroize. But then going from 1 to 2, it has a skip connection and not a convolution. So it has an average pooling. Having a skip connection or an average pooling both seem to be not so good choices. Instead, in going from 1 to the output, it has a 3x3 convolution, which does not seem to happen. So there are some interesting things coming up when looking at the architectures in detail. Whether this is so conclusive, hard to tell, right? So you think you get some insight. Okay, so now how can we maybe find out in a more closed form solution on how to learn about that? We can of course do math. So this is now an evaluation of standard neural architecture search methods, starting with bananas, which is like this path encoding, and then running Bayesian optimization on the path encoding. Usually one of the state-of-the-art methods if you allow some like few queries for your model. And then this works quite well. And here we just optimize directly single objective on the robust accuracy. And then these are the numbers of the optima. So on clean data, 94.68% on FGSM, the optimum, like the best possible value you can get is 69.24. Then going down for the harder attacks and for squares, it's a bit higher. You can also see that for common corruptions, the values are in the same range as for PGD. So it's not like from the plain numbers, these are not so different in their behavior, and one impacts the other. So here we have been running these simple NAS methods directly in order to optimize for models to become robust, and we can find robust architectures by that it works. So they're really transferring these simple methods, and you can see that this bananas encoding, path encoding, simple, straightforward, that works well on clean accuracy, also works well for robust accuracy, coming quite close to the optimal. Yes, please.
I'm not sure whether this is the correct point in time to ask this, but I mean, you explained very nicely what are the common components in the cell to improve robustness, I guess, or ensure better robustness. Did you also kind of look at it from the other direction? So taking one of these very well performing cell configurations, what screws up robustness the most? Is there like one thing I can kind of introduce to make everything bad?
Not sure I found that pattern. Yeah, not sure. I mean, it's like the cell spaces are small, so this is why I'm not so confident here, because I mean, if you change, like if I want to change one operation to be a zero operation, then I can say this is not bad because I have a zero here, but it's maybe also bad because I'm missing a thing somewhere else. So I think it's hard to be sure about that. But I mean, I somehow tried to reason about it here, right? So like having skip connections here in the brown parts and having the convolutions going directly from input to the output, like building a wider network seems to perform worse than building a deep network.
Yeah, okay, I guess you mentioned that, yeah.
Would it also be worth it to investigate what impact does it have to have certain operations in certain places? So what are their contributions of a certain operator in a certain place, or the condition of them?
Would be very interesting. Do you have an idea of how to design the experiment?
I mean, this is not my area, so
No,
maybe what I will say is
no, it's
not a good idea, but I was thinking of Shapley values that are used for game theory as well. Maybe this could be because I think it's very interesting, but you only have the, if I understand correctly, on the y-axis.
Maybe you're right, since we have a tabular benchmark, you could start with game theoretic approaches to analyze. We have no problem about that, but it's a good point. Yeah, interesting. Yes.
What would you recommend? So in your result paper, you still show that there is a huge gap between what NAS is able to find and the true optimum, what could be found.
Yes,
maybe we need to go to also deep learning pipelines, incorporating mechanisms to ensure robustness, like the data precision, or.
Yeah, I mean, these architectures are all okay. There is a lot of room for improvement. One is obviously these models are pre-trained from NAS Bench 201. They are not adversarially trained, and yeah, it's randomness in how models behave when you train them. So here we're looking at aggregate numbers because we hope that if we look at many models, we can analyze them. We can see the signal coming out from the noise. But if you look at every element, I would argue that it's probably noisy. Because you initialize it differently, maybe your absolute number will be slightly different. I'll show some results with another search strategy. If I'm not sure I'm going to time for that, but I have some slightly better results as well. But in the end, I think when I look at these numbers, I find it already impressive how well we can predict that. It's not that trivial anymore, right? So for this standard thing, NAS Bench 201 on accuracy, the question is usually how many queries do I need in order to give you the total optimum? And now this task has become much more interesting. So we cannot easily tell you this is the optimal architecture anymore. But yeah, I mean, you can get slightly better results. I mean, bananas really is path encoding, it's a strong encoding. But it does not learn anything about the target when encoding the data. It's really learning similarities between them.
Do you remember how many function evaluations you allow for each run? For random search, how many queries?
Oh, yeah. It's the same in all three, but I don't recall actually. It's one of the standard values you usually have. So you start with 16 evaluations, usually for BO, you give it an initial set of 16, and I would have to read it up in the paper. What I like the last content thing I wanted to talk about are zero cost proxies, just preparing the stage for Gavin's presentation later on. So I mentioned in the beginning that there's two ways of making this prediction-based NAS efficient. One is to actually train a predictor that is trained on very few samples, and that will give you a good value, like a good idea of how robust something is going to be. The second approach will be to evaluate actually zero-cost proxies that are usually run on a single batch, maybe. So maybe you get a single value from your data, just ask how many parameters does the model have, how deep is my model? So this can be a zero-cost proxy, but it can also be something like you run a single batch of your data and then you measure the curvature or the Jacobian of your optimization surface after this one run, and you predict whether this is going to convert to something meaningful. And then, of course, there are pruning-based methods that would approximate the change in loss when you remove a single operation. Yeah. So there is basically a zoo of such models, model predictor zero-cost proxies that have come up. Here is a small, incomplete, like very incomplete list of references. And yeah, so the core idea is to get some insight on how an architecture is going to behave just from running at most one batch of data. So being very cheap in that part. Yeah, and then Jacobian-based and Hessian-based methods somehow look at the optimization surface. Other methods look at the amount of nonlinear subspaces in your network, or here, as I said, pruning-based methods would basically see the change in loss when I remove a certain operation. And then there are these baseline methods that really look at plain numbers that you can get from your model directly. So now the question is, like, when I look at these, how would they correlate with my robustness? So here you see the Cannon-Tower correlation for these Hessian, for a approximation of the Hessian operator from the model. So an approximation of these, like the optimization surface curvature. And interestingly, there is no really clear pattern, right? So for FGSM, there even seems to be a negative correlation and a positive correlation for many other attacks. The interesting thing is that if we consider the pre-trained model, like the first row is pre-trained, and third row is pre-trained, and then the second and fourth are the random initialized models. You see that the behavior flips. So on the randomly initialized model, the correlation for the Hessian is actually positive everywhere. However, if you take a trained model, this is entirely different. So this is a bit scary. We can reason why this is the case. So for example, you can argue that if you run your initial sample on your initialized model, you want the optimization surface to give you a good gradient, so steeper is better. When you're close to the optimum, you want your robust model is usually to end up in a shallow optimum, where small changes don't matter. So this is why the correlation at some point will flip. That also means if we're looking for robustness, maybe we have to be careful with these, because behavior is a bit hard to predict. Okay, then we evaluated many more of these like zero-cost proxies. Here the symbols indicate what kind of a predictor it is. So Hessian-based, Jacobian-based are these red stars. Then pruning-based are these blue diamonds. And then there are the baseline methods. And yes, there is some positive correlation with most of them, but it's also, again, a bit mixed picture. And for FGSM, it seems to be quite well correlated. But then if you look at higher attacks, APDD, it seems to be quite hard to predict what is going to happen here. So we did some experimental setting in order to see how much information is in these zero-cost proxies, which is we stacked all of them into one vector of features. So every zero-cost proxy is super cheap to compute. We can create a long feature vector, having every scalar value for every zero-cost proxy, one after another. We feed them into a random forest in order to learn a prediction. And this will allow us to, in the end, see how well we can predict, like regress the prediction, like the robustness of the model. It also allows us to do feature importance. Now, I don't have time to talk about feature importance here, but what I'm going to show you is quickly the numbers you get for the zero-cost proxies. So So on clean data, first of all, this of course works really well. We know that the zero-cost proxies have been designed for clean data, so here they perform really nicely here with accuracies, yeah, far above 90%. And then if we use the zero-cost proxies to predict on like single objective, just on the robust accuracy, their prediction accuracy drops, and drops the harder the attack becomes. So then it becomes harder to predict. When you predict like in a multi-objective way, like a two-element vector, clean and robust accuracy, this also still seems to work, and you get an overall prediction value that is somewhere in between these two. This is kind of okay. An interesting observation that I did not have time to present here in detail is what happens, like which features are important. And the interesting thing is that on the clean data, to reach these high values, usually the feature importance can focus on one of the features. So one of the zero-cost proxies, or very few of them, are enough to be very precise in the prediction. While for the robustness prediction here, to reach these numbers, usually the random forest refers to many of the zero-cost proxies. So it actually leverages the signal across these and doesn't look at only one, but it needs to have the spectrum of very few. These zero-cost proxies seem to be very helpful, but we cannot just use one. We need to get more information on the models. Yeah. Now, if I would have been talking faster, I would have told you more about one paper that we proposed to do mass from a generative perspective with the multi-objective optimization. Roughly speaking, the idea is really just to not like to start from here, but not learn a reconstruction loss, but just directly learn from the space to generate data and train the latent space such as to generate directly data that is likely to perform well in practice. To do so, basically, we had to make this graph-based generated differentiable, so it allows for end-to-end learning, so we could backpropagate everything through that encoder. The references here, presented this last year at ECCV. And the nice thing about it is that, so if you look at the overall architecture being given here, you start from a random sample, you generate an architecture, or basically you generate many architectures. You're going to predict with the very cheap graph-based predictor which ones of these are good. And then based on your own predictions, you retrain the latent space to give you these good models with the higher likelihood. This based on a weighted retraining strategy that had been proposed by Tripp et al. In 2020. And that comes in very handy if you want to really optimize your latent space, not optimize within the latent space, but optimize your latent space. So I can recommend to look at this reference whenever you feel like creating a latent space that very likely gives you something that you want. Okay, we evaluated this on many data sets, and I'm going to skip this entirely. So basically, this gave us very good architectures and very query efficient architectures across all the image-based search spaces. We also tried the NLP search spaces. Yeah, so the R curve also was quite nice. Yeah, so this behaves nicely and in particular give you good results at very few queries. But what it can also do is evaluating multi-objectives. So basically, you can now optimize your latent space with respect to not only one objective, but with two objectives, and then you can do joint optimization on top. In the paper at ECCV, we showed this on the hardware awareness benchmark. So with examples on optimizing model latency and accuracy, or optimizing model accuracy for a given hardware latency, where again our results were quite promising. But now this is a plot that I want to show you. This is basically now applying this method on our own benchmark. that basically evaluates robustness, and here the optima that from the Pareto front are given as the yellow stars. Then you see two results here for our model along the Pareto front. One are these blue crosses here. This is just a plain application of our model on this data. And then, I mean, as you asked before, I mean, there is some improvement to be done, right? So we don't find the optima. We wondered what could be the trade-off, and you notice that clean accuracy and robust accuracy are correlated. So what we did to improve the process is to apply a whitening of the target values before, and that allowed us to get these improved results in prediction. We get dots, and this is really results like from last week or so. So Eureka, first author of this work, just gave them to me last week to be able to show them here. So yes, multi-objective optimization works quite nicely, but you have to think about the correlations in your data, and if you want to do some Pareto front optimization here, and your data is correlated, it's better to remove the correlation as well as possible before running the optimization. Okay, and then I'll come to the conclusions. So in general, we've seen that even well-performing models can suffer from low robustness and generalization. And so it's important to think about, like when I want to apply any model in the world, I want to think about what happens under noise, under corruptions, and how well this is going to perform. We've also seen that robustness can be improved if I augment my training data, or if I regularize my models. But neural architecture properties as such also relate to the model's robustness, and we should have this in mind. And then conducting neural architecture search on robustness of models or with multiple objectives on robustness and clean accuracy can actually give us insights on the important properties of neural architectures that make them more robust or less robust, so to say. Yeah, and the good news is that zero-cost proxies can still be helpful in this domain, so they can also help us hopefully to be really fast and very efficient in the future. But they perform differently when applied to NAS for high clean accuracy than when we apply them to NAS for high robust accuracy. So we cannot just directly transfer them. We could think about it and maybe evaluate on which correlations to hold or which correlations will turn into negative correlations. And then thank you for your attention.